So in this little video, I hope to show you the difference between object-oriented and imperative and functional programming, and thereby to give you some motivation for it. I also aim to introduce some vocabulary so you can actually benefit the most from the examples. So let's first do a little reminder of what the situation is when you do a computation on your computer. So I had this little picture of the von Neumann model, which always involved data and action. And when I introduced functional programming, I compared two different ways of programming. So first I unfolded this. So I emphasized that there was data in different states at different time, and that we were transitioning between, so different variables were transitioning between different objects were transitioning between different states. So this is what happens on the computer. And then the question is, how do you write the code so that in the end, this is what happens? So in the code, what do you want to emphasize? And I highlighted two different things. So the first one is imperative programming, which will decide to highlight intermediate states. So this means that you will tend to name a lot of variables here. You tend to give a lot of names to the data. And at any point, you have a precise idea of what the state inside the computer is. So the emphasis is on the data. And then I also had talked about functional programming. And functional programming was emphasizing the transitions. So these actions. Of course, those are also, the functions are also objects in memory. So they also have to be written somewhere on the computer. But the emphasis is on those transitions and on combining those transitions into more complicated ones. Okay, so this was the little reminder of imperative versus functional. So in yellow here, you have the functional, and in red, you will have the imperative. Okay, so let's now see how this changes with object-oriented programming. So with object-oriented programming, it's still this same picture, of course, of some data on your computer, and again some data, and again some data, and some transitions on the data. Okay, some different functions that you can apply. Now, the decision that is made with object-oriented programming is not to highlight either functions or data, so either data or actions on the data, but it's to group data and actions on that specific data. So in object-oriented programming, what we tend to do is split up this part with respect to this one, and then look at, so actually this should not have been written here, so group all the data with the relevant actions. So cut up a whole space of data and actions on the data into different bits. And in the code, we try to structure the definition of the data with the definition of the function acting on that data. So it sort of makes sense. If you have a string, you want to know how to lowercase the string, or how to uppercase it, how to reverse the order. All those things are dependent on the fact that you're looking at a string. So the code for all these things should be close to each other. If you deal with a person, their email, their project submissions, their age, information about the person, any code that deals with information about the person should be grouped together. So that if you are a bank, say, and managing bank accounts for people, then you can have one part that deals with the person, their contact information, their marital status, their tax information, and then another part of your program, of your code, that deals with bank accounts and transfer of money between bank accounts and things like that. And you see that each time I talk about person or I talk about bank accounts, this involves simultaneously saving some data about that object, but also performing actions on that object and on that data. So that's the point, is really you try to organize your code with objects, so with data and actions on the data close together. The goal is to make for easier to maintain code and easier to use. So a little glossary now. So some words you need to understand. The goal of object-oriented programming is to define data types, but not just a bunch of data types that are very relevant to what you're actually doing. So I give some example. A person, a bank account. If you were to program for a bank. Now, for each of those data types, you want to define an interface. And the interface, if you want, is the public side of this data type. What this data type advertises to the rest of the code and encourages other parts of the code to use. And the importance of the interface is that this is separate from data structures, algorithms, and code that are given inside the data type definition. So these data structures, algorithms, and code are important to actually do all the actions that the data type is supposed to realize, but that's completely irrelevant for an outside user. Someone writing another part of the code that will require sending email to a person, right, does not need to know about how this is actually done. So let's look at an example. If you are using your credit card while you are in a foreign country, and if that pattern is not very usual, you might get an SMS warning you that this is not a usual pattern. So at some point, the person that is flagging that, or the part of the code that is flagging that this transaction is suspicious, should not have to deal with how to send an email. This is going to be, or how to send an SMS. This is going to be in another part of the code and should be attached to a person rather than a bank account. So this whole idea of creating an interface and isolating the data structures, the algorithm, and the code from the rest of the code is called an abstraction barrier, and it's bringing encapsulation to the program, also called information hiding sometimes. Now, in Python, this is done with classes. So a class definition will, in Python and many languages actually. So a class definition will consist of the definition of some data that is associated to the class. So those are called data attributes, and several functions that are called method attributes, or simpler methods. Now, what do classes do? Well, they support two types of operation. Instantiation, so creating new instances of the class, new objects of that type. You're a new client in the bank, you need a new entry in memory for the bank or in a database. So you need to create a new object associated to this new client. And also, the classes support another type of operation, which is attribute reference. So access to class attributes via dot notation. So if you have that client object in memory, you might want to access information about that person's age, marital status, or send that person an email. So you might want to access data or execute some operation. And this you do via dot notation in many languages. Now, how do you construct those data types? Well, mainly using two different tools to define those attributes, and those are called object composition and inheritance. So we'll see object composition this week and inheritance next week. Okay, so this was for a quick introduction to general principles of object-oriented programming as it is understood in many languages like Python, Java, C++, etc. And in the next little video, we'll see a generic example of a Python class. So what to look for to understand what this class is doing.